So we're going to remember from yesterday that we had these two equations. This one, which was the slope equation for acceleration. And then we also used areas to develop this one. So these two tools are quite useful. But you'll notice that every equation we have so far has a t in it, a time. They all depend on time. So it would be nice if we could develop an equation that didn't have time involved in it at all, because there may be a situation where we don't know the time. So what we're going to do is use these two equations and we're going to blend them together. Okay? I guess what you could think of it as is you're solving a question where you had to do two steps. You had to first use this first equation to get a time, and then use the time in here to say get a distance or a speed or something. You could do it two steps every time, but we're going to do two steps once, put them together and get an equation that will allow us to do it all in one step. And this process is actually very similar in a simple way to what physicists do. They take equations and manipulate them towards a certain end to see if they can discover something. Okay. So if we start with the first equation, what I'm going to do is rearrange it. I'm going to multiply both sides by t, first of all, to get that. Pretty straightforward. And then I'm going to divide both sides by a, so I've isolated the t. Then I get something that looks like that. You can do that, right? That's what's allowed. Now, I'm going to take this thing here, which is actually equal to t according to my equation, and I'm going to bring it up here, and I'm going to substitute that into this other equation wherever I see the value of t. Because it's equal to t, so I can do that. It'll be a little messy at first, but hopefully we'll be able to get something that's not quite so messy if we work with it a bit. So here's what it would look like. V1. Now instead of t, I write V2, take away V1, divided by A. Okay? And then plus, multiply there, plus 1/2 A, and again, where the t is, I write V2 minus V1 over A, and of course that is all squared. So far so good. Now we just have to use our algebra skills to simplify this equation, to make it a little simpler. So the first thing I'm going to do is I'm going to do some multiplying. You recall that, remember, if I multiply V1 here, I have to multiply it by the first term, and then I have to multiply it again by the second term, right? And that's how we distribute. So we'll do that part. So D equals V1, V2 is the first arrow, and then minus a V1 times a V1 is a V1 squared. So I end up with that. And of course there's still an A on the bottom that I didn't touch, so I can't forget about the A that's sitting underneath. If you have questions about the math, stop me anytime. Now, over here what I'm going to do is I'm going to square those big brackets. I'll leave this part. I have to square this. So what I'll do is over here I'm going to write a little aside. Just in case you've forgotten, V2 minus V1 squared is V2 minus V1 times itself. And the way we do that is we do FOIL, right? First outside, multiply that, and then multiply it by the other one. And then we take the inside guy and we multiply him like this, and we multiply like that. That's how we do that. Remember that from grade 10? Okay. So if I do that over here, what I'll get is I'll get V2 times V2 first. And I'm going to put all this sort of in brackets so it doesn't get messy. So there'll be a V2 times V2, which is V2 squared. You can follow over there, and you can see how I'm doing it. Now I'm going to do two steps at once here, because you guys are experts. If you look at the second arrow, say this one right here, it produces a term, oops, no, that's the first arrow. Sorry, forget that. Look at this arrow right here. It produces a term, negative V1, V2, when I multiply this and that. But then when I do this part down here as well, it produces the same term, negative V1, V2. So I'm just going to group those together and I'm going to write it as 2, so it will be minus 2 v1 v2. So I did 2 steps in 1 step, okay? A lot of you do that anyway, because when you do FOIL, you know that that's how it works, right? All right. Then the last one is v plus, because it's 2 negatives multiplied against each other, v1 squared. And on the bottom of that fraction, I must also square the bottom, because you have to square the top and the bottom because of the brackets, a squared. So there, I'm taking care of the squaring, and I have this. So far, so good? Okay. Next thing I'm going to do is I'm going to combine this 1/2 a part. The second term is still messy, so I'll leave the first part just as it is without touching it. v1, v2 minus v1 squared over a. And I'll clean up this part. I'm going to do a couple of things here. First thing I'm going to do is I'm going to look at the a's. I have an a on top and a squared on the bottom. So if I divide top and bottom by a, d will disappear, and this will just be 1a, right? So far, so good. And the other thing I have is a 2, which I multiply over on the bottom, and a 1, which I multiply through on the top, which won't change the top at all. So I also notice I put equals here, which I shouldn't have. That should be plus, so we'll fix that. Okay, so let's do that. 1 times the top is just the top. And then the 2 goes with the a that's left on the bottom, and the whole thing turns into that, right? Simplify. Now, it looks like I have 2 fractions with an adding sign in the middle. And so in order to add fractions, you need a common denominator. So it looks like if I multiply the first fraction by 2 on the top and the bottom, I'll create a common denominator of 2a. And so that's what I'll do. I'll multiply this one 2 on the top, okay? So it's 2 times the top, which means the whole top, 2 times everything on the top. The top turns into that when you multiply it by 2. And then the bottom turns into 2a, like that. And then over here, we've got v2 squared, all the same. Nothing changes here. Okay, and now we have to think about what we can do next. And what's really bugging me is having to write these stupid fractions all the time. I'd like to get rid of the fractions. So it occurs to me that if I multiply everything by 2a, fractions will be gone, right? So let's do that next. Let's multiply everything, and both sides of the equation. That's the rule. So 2a on this side becomes 2a times d, and then when you multiply 2a times the other side, all these little terms just become, the fractions disappear, in other words. So we get this. Okay, so far so good. And all we have to do now is sort of collect the like terms. So the first thing I notice is if I look right here, I have a positive 2v1 v2, and over here I have a negative 2v1 v2, so they subtract and it becomes 0. So those are gone, which is nice. And then if I look over here, I've got negative 2v1 squared, and I've got a 1v1 squared. So if you put them together, that's negative v1 squared. So this becomes 2ad equals negative v1 squared. And then, of course, we have the v2 squared that is still left that I didn't touch. That's a lot simpler. And we rearrange this equation a couple ways. We move the v1 squared to the other side of the equation, so it becomes plus v1 squared. And that leaves this. And, of course, the way we write equations, if you put that in the mirror without changing anything, it'll just be this. So this is how you see it in all the books. It's the same exact thing, it's just looking at it backwards, right? And so this equation now is quite simple, and we can use it whenever we have a situation where there is no time given, but it still has the a and the v and the d's that we need. And again, it's a good illustration of this process of manipulating equations to get to something that you want, which is basically what physicists do for a living. Okay? Any questions about that? So this would be equation number 5. And so what I'll do now is just do a quick review of all the equations that you should have on your formula sheet so far. Okay? So the first one is our good old-fashioned d equals v times t. Put that here. And of course, you can use this in many different forms. The other form of this that we talked about was how velocity is the change in displacement over the change in time. But those are both really one equation, right? They're not two new different ones. And that is the equation that we use when we have constant speed, remember? Because there's no a involved. If we have accelerations where speed is changing, we developed a new equation, a equals v2 minus v1 over t, which basically says it's the change in velocity divided by the change in time, right? It's a slope equation. Then we discovered that using areas yesterday, we can get this equation to work for us. And this involves finding displacement. And I should point out, I'm not going to go through all the math of doing it again, but this little guy has a twin brother. And his twin brother looks like this. I'll put him in red beside here. D equals v2t, take away 1/2 at squared. We seldom use this guy, but he exists. Very often you don't know much about v2. It's usually the thing you're after. But if I just show you briefly the graph that we used to do this, remember it was this. And so what we said was, we'll cut it up into two pieces, a green rectangle and a triangle, and we'll add them up. And this was the area of the rectangle, and that was the area of the triangle. But we could also do this little trick. We could look at the whole area. This is v2 up here, and this is v1 down here. We could take the area of the entire blue square, which would be v2 times t, right? And then subtract this triangle, which happens to be exactly the same as this triangle, and there it is, and we would still get the exact same area, exact same number. And so you can also use this guy, and so we'll write it on our sheet, and we'll have him handy just in case you hit a question where you're like, they're giving me v2 this time, and I don't know what to do. Maybe that's the answer. So here, there's him, and then we have our little friend that we just figured out, v2 squared equals v1 squared plus 2, whoops, what am I doing there? Let's do that again. v2, hang on, my finger is going faster than my brain. v1 squared plus 2ab. Now, there are also two other equations that we talked about. All of these equations involve speeds that are either changing from one to another, but in a nice straight line. But they don't look like the trip to Sudbury that we talked about, where the speeds were all over the place. So we also looked at, and I'll put these in a separate box, if you have a trip where on your graph, your speeds are all over the place, like when you're going to Sudbury, what we sometimes do is we average out the speed, and it's the total displacement divided by the total time. So we also had this equation. This one is the speed one, no directions. And if you add directions, you get the average velocity. I'll put the little signs on it. And it's the total displacement over the total time. But these two equations are kind of for something different. They're for smoothing out a trip with lots of different speeds in it, right? Whereas these other equations are more for much smaller trips where something is just changing from one to the other and that's it. So we won't use these very often, these average ones, but they're there, and again, they should be somewhere on your sheet. And that's where we're at for formulas so far. So we'll stop there. And we'll do a separate video for the next two parts because it's a little bit totally different than this.